Described below are three cases where advances in materials technology have permitted material replacement in existing products or processing. Alright. So highlight the characteristics of advanced material being used and discuss the main motive for the replacement and the limitations for each case. So there's three cases as being shown A, B, C. Alright, and they will ask to actually talk about how advances in materials could actually replace them. Alright, in a sense. So therefore the first one is orthodontic braces, alright, for teeth corrections. And why do we use super elastic nickel titanium against conventional stainless steel? So what is it all about? And if you were to remember, this is actually being discussed back in previous parts. I think it's in v10.8, nickel titanium alloy shape memory properties. Alright, and deeper approach in explaining shape memory. I think it's either one of them. It's not both of them. It's this one, 10.6. Alright, dental application. Alright, super elastic alloy dental application. Alright, is yeah. And therefore just a briefly thing talking about it. So this is the wordy answer. Alright, and you also need to include graph which I'll draw later. I just want to someone go through is that undergoes very large deformation due to phase transformation between oxenite and metastatic microstructure. So this super elastic metal undergoes very large deformations, alright, due to this type of graph. This is a strain, this is a stress. Super elastic is that when you pull, alright, you can have this type of curve that is coming out, alright, and it will increase all the way. This is when you start to pull, loading, and when you start to unload the forces, you actually string back into its original shape. As you can see, there is no strain, alright, because it will go back to its original shape. There is no strain at all. So you also need to define this type of graph that is coming out. Alright, and also the lecturer says that it would be best if you were to also draw the normal somewhat metal, the graph of a metal, other metal graph. Alright, so this is I don't know what he have drawn, but he have somewhat say U point, not Uling point, sorry, and then normal method. So if we want to draw the normal one, the normal metals, not normal method, that should be normal metals. Alright, where this is maybe I should draw it better. So give me a while, really. So the normal method will go like this, okay? And then over here, this is the Hooke's law, right? It's linearly. Up to here, you'll become non-linear, you'll strain, right? So over here, maybe I should draw. This is the strain. Amount of strain, I should say. And then over here, you unload. Okay? And unload already, it will not deform any. You will not go back to its original shape. This is the original shape. This is the deformed one. And then over here, you can also write permanently deformed. And you can also just draw straight away, alright, from this two graph. Alright, give me a while. If you were to put this graph and this graph together, alright, so in other words, you superimpose. So you put this shape onto this. So this is a form of superimposing. Alright, just to expose you to more words, superimposing. Alright, you'll get this. If you draw this thing, you'll get 2 marks. Alright, that's what he says. And advantage of this type of nickel titanium super alloy is super elastic alloy is that it's 10 times more elastic than the steel wire and requires lesser adjustment, which could incur pain on the tooth ligament. Alright, so over here is so this is your kind of your teeth. Then maybe you could say that this is your tongue. Alright, anyway, so you have your braces, alright, placed on top somewhere over here, right? So some of it, and then you hook the wires through this so-called things that is attached to your teeth. I shouldn't have said that it's a bracer, but rather than some metal stuff that is attached to your teeth. I never go through braces before, so anyway. Yeah. So over here you tie onto some, I don't know what the hell, but you eventually put a force in this direction and this direction. And if happen that if you were to do that, alright, this teeth over here will start to, alright, give me a while, sorry. It will start to adjust. Alright, start to go nearer. Meanwhile, the rest of the teeth will also be going nearer. And eventually, all this thing over here will go nearer. Alright, you see? So you close up all the gaps. Maybe I should also, give me a while, I put it, you kind of close up all the gaps, so your teeth will be nicer. Alright, so in the exams, you will want to also draw this type of things that is happening. These are the forces. You can don't draw the red color one that I've drawn, because I don't think the lecturer have drawn it, but I just drawn it due to prior knowledge, so I may be wrong also at this part. So if you want to draw, you draw also, and you can label that as a gap. Okay, this is it. Alright, and if you also want to talk about the ligament, alright, I don't know what the lecturer never draw, but if you want to draw. This is the tooth. Alright, this is your gum. Alright, so the ligament is actually underneath the bone. Alright, so these are ligaments. So if you were to move your teeth, in this manner, you have to move it out a little bit. Okay, your ligament will actually shift a bit. So maybe I should have drawn. So if you were to move your whole teeth like that, alright, the ligament will actually move as well. So you're actually pulling onto your ligament that is attached to your gum, and therefore this ligament over here will actually be feeling pain. So less adjustment will cause lesser pain. That's what it's trying to say. Alright, and then limitations: high cost, limited stress. Alright, control fatigue. Alright, so high cost meaning the titanium. Alright, and limited stress is talking about how very hard to manage or control your steel, your wire, because it's very flimsy, right? So if you want to because there's a hole over here in the middle, if you want to put this wire into the hole, it's very flimsy, and therefore it's very hard to slot it into the hole, and therefore there's a problem in there. Okay, control fatigue, I think is advantage. I don't know why you put under disadvantage, but anyway, control fatigue itself is to control the fatigue, to prevent fatigue from happening, I guess. I don't know. You can search, but I can't search any good answers. You can do it yourself. And other applications can be thermal sensors and actuators that you can talk about it. And we also want to, over at this graph, you also want to highlight like percentage of strain. Or nonetheless, you can follow this graph over here, but it's not fully expressed well. So maybe you can also draw it better. And I think this is it for this first part 1a. Alright, why do we use nickel titanium alloy to replace conventional steel? Okay, so in the next video we'll talk about why do we use, for transfer films, why do we use some other stuff to replace some other stuff. So I shall see you there in the next video.